Hi, my name is Dhruv, and together with Maryam, we'll be talking about noise tomography and fermionic simulation, specifically how you can extract the noise channel from a fermionic encoding onto a digital quantum computer. So just as a general outline for this presentation, we're going to start with some motivation as to why you would want to do this and what can run on NISQ devices, followed by a brief explanation of the model we're trying to implement, the Fermi-Hubbard model, how you encode it, along with the method that we are using to extract its noise channel process tomography, applying it on both certain error models as well as noisy quantum state vector simulators and probability-based simulators, and our results from that. So just ask for some motivation. We are currently in the NISQ era of quantum computing, the noisy intermediate scale quantum era, characterized by a low number of qubits, low connectivity. Some connectivities of some systems are only next neighbors. You can't say entangle qubit 1 to qubit 7 without a chain of swap gates, as well as low fidelities. Our current best fidelities are hovering around 10 to the negative 3, as well as a low coherence time. This means that many of the subroutines we explore in 657 aren't physically realizable on current QPUs, such as, the quantum Fourier transform and phase estimation. So this leads to the question, what can we conceivably run on today's quantum computers? And this comes down to what models are easily mappable. There's one family of models that people have been exploring. It's to do with quantum combinatorial optimization. Basically, if you have m clauses and n bits, find an n-bit string that maximizes some sort of cost function or chain of cost functions. An early implementation of this was QAOA. But Maryam and I, we love physics. So are there any interesting physics models that we can simulate using quantum computers, or at least as toy problems we can run today? And there are. It's interesting because many solid state models, so solid state mechanics is the field that analyzes how materials behave under both internal and external stresses. Many solid state models follow a pattern very similar to QAOA problems, where you have a function with some cost and you're trying to represent this function. So one example is the SSH model, which is a good model to describe the conductivity of some polymer chain. But crucially, it assumes non-interacting electrons. And so when we analyze a material, we like to look at the electrons in the system to describe the behavior of the system. So what if we want to account for the fact that electrons do interact? Well, that brings us to the Fermi-Hubbard model. That's why we are interested in seeing, can this be physically realizable, amongst other things. For a bit of background, you can model a object, or you could model a solid as positive charges with a sea of negative charges flowing around. These negative charges are carried by electrons, and electrons obey the Pauli exclusion principle, which means that two identical electrons, or fermions in general, can't occupy the same quantum state. And if you exchange two fermions, there is an overall minus sign. This minus sign is different to the fact that different Paulis anti-commute locally, but it's used. We use this fact to be able to encode fermions into qubits and sets of gates. So the Fermi-Hubbard model, just as a background, was initially developed to describe electrons in a solid, and it has a wide range of applications. It itself is an approximation of solids, as all these models are. In general, it describes the transition between conducting and insulating materials. How this model works is that you have electrons at these different lattice sites, as if there are electrons in the sea, except now we have electrons that can only be in this lattice, and they hop between different points in this lattice. We are going to consider the case that they only can hop between their next door neighbors, the electrons' next door neighbors. The Hamiltonian of the system, or the energy of the system, the function that governs the behavior of the system, is characterized by a kinetic energy term that describes how electrons hop between different sites. This hopping is described by two operators, an annihilation operator and a creation operator, which is B dagger, which describes the electron moving from one site to another. And we also have a repulsion term, because remember, we want to consider the fact that electrons repel one another due to their charge. And so this accounts for that. But two electrons can only occupy the same site if their spins are opposing, because remember, two fermions with the exact same quantum state cannot occupy, you can't have two fermions with the exact same quantum state, and so the spins must be flipped to be able to have both these electrons at the same site. So this is our general model that we're trying to simulate on a quantum computer. And so how do we map this to a quantum circuit? This is where the Jordan-Wigner transformation really comes in and shines. So the Jordan-Wigner transformation in general is a method which maps fermions to spins. And if we can map a system in terms of the Pauli spin matrices, we can implement them on qubits. That's why we're using this transform, and that's why it's being used. For this explanation, we're just going to focus on a 1D chain of, an electron can only hop, between in a 1D manner, but it scales quite easily to 2D. So our steps for, in general, when we want to transform a physical system into a spin system is to first identify the characteristics of this system. As we explained before in the previous slide, fermions are characterized by annihilation and creation operators that essentially govern whether there is an electron in one location or another. These operators anti-commute. And we also have a system over here where up represents whether a electron is unoccupied at a site, and down represents whether the electron is in the site. You can think of it as 0 and 1. If this term is a 0, then it means that an electron is not at that location, and 1. If it's a 1, it means that, hey, there is an electron in this location, and 1, and the state describes where the electrons are. So using the fact that the annihilation and creation operators anti-commute, you might think that, okay, let's take the creation operator and map it to a Pauli spin plus operator. Since it makes sense, a spin plus will take something from 0 to 1, and let's take the annihilation operator and let's associate it a Pauli minus. But this is not in fact the case, because remember about the fact that because of the Pauli exclusion principle, because these terms anti-commute, you must obey odd parity. So for example, if I have the state 1, 1, 0, 0, i.e. there are electrons in the first two sites and no electrons in the second two sites, and I apply the lowering operator on the second site, applying the lowering operator on the second site means I'm getting rid of the electron on the second site. So the state is 1, 0, 0, 0. But because of fermions obeying odd parity due to the Pauli exclusion principle, we need to add a negative sign to really make sure that our spin system is representative of our physical system. We also define these gammas. We just define this in a way to make it easier, since sometimes when you map things in terms of annihilation and creation operators, it becomes quite large. So we define, gamma I to be the annihilation plus the creation over 2, and then the negative version of that, and permutations of it as well in terms of z and x and z and y. This will be helpful later on in the presentation. So this is just the same thing as the annihilation and creation operators, just a different way of representing them. If we look at the scaling of this mapping, so for example, let's take this mapping that we have on this previous slide over here, and let us apply it to a 2-mode example. We go from this Hamiltonian over here to this simple Hamiltonian over here. And in general, we can say that this encoding is efficient and correct because in this case, a one fermionic operator corresponds to a linear number of qubits, or the number of qubits you have in your system, right? So we have a 2-mode example. So each operator corresponds to 2 spin operators. And so it's only a linear relationship. And as a result, a polynomial number of orbitals that we're trying to model corresponds to a polynomial number of spins, and that's okay. The way we ensure that our mapping is in fact true to the physical nature of our system is to look at the eigenvalues, and we see that the eigenvalues of our spin Hamiltonian is the exact same as the Hamiltonian of our initial system, just off by a factor of h bar. So this mapping is correct because the eigenvalues are also retained and it's efficient as well. Now we get to the idea of process tomography, which Maryam will continue.
Okay, so Dhruv gave like an introduction of the Jordan-Wigner transformation. I'm going to talk a little bit about process tomography, which is useful when you're trying to understand what noise your system has. So in particular, we saw in class that the operator sum representation and Choi matrix representation are useful when you're trying to characterize a quantum channel. And for CBTP map, we already know that they are equivalent. So another way which is useful for characterizing a quantum channel is in terms of a process tensor or a chi matrix, which is what we are going to be using in our presentation. So the idea is that you can express any quantum channel in terms of these chi of the chi matrix as well as these EI and EJ elements where EI and EJ are simply the Pauli basis elements. So for instance, for 2 qubits, an EI would correspond to like any element from II, IX, IY. And in general, this chi matrix has size 4n to the power 4 to the power n times 4 to the power n. So this just scales with the number of qubit basis choices that you can have. So the general idea of doing process tomography is that you initially prepare your input basis states and then you evolve them through the circuit. And then the basis that you're measuring them in is in the Pauli basis, as I already mentioned. And then because your data may not be exactly in that direction, you use a tomography fitter, which reconstructs the quantum channel. The one issue with process tomography is that it's an expensive process because it scales exponentially in the number of qubits. So this is not exactly a scalable method, and it also does not account for spam errors, which is the state and preparation measurement errors. But for now, we ignore this because we are running this on small systems. So before we actually do a process tomography of the quantum channels on our IBM 9Q devices, let me just say a little bit about the error model. So one thing that we can do is just look at what the fermionic error model, fermionic error channel would be if we know what the error model is. So let's say we have the depolarizing noise with these Krauss operators. So if we do an inverse Jordan-Wigner transformation, we get the following Krauss operators. And as you can see from here, the K1 and K2 operators are non-local in terms of there's a non-local number of gamma bars, and the K3 operator is a local operator. So it looks like you have a local noise channel on the qubit side, but on the fermionic side, it corresponds to something that is non-local. So let's see that if we do tomography, do we get something similar? That does local noise map to local noise on the fermionic side as well? So before we start this simulation, we want to make a few things clear for ourselves, that we know, as Dhruv already mentioned, that we have fermionic anti-commutation relations. So when we are doing this just Jordan-Wigner transformation, you want to make sure that our encoded operators are also anti-commuting. So for that purpose, our encoded operator corresponds to U1 and U2. And this the idea is that when you multiply U1 and U2 together, their encoded versions should correspond to identity. So the quantum circuit that corresponds to U1 and U2 in the qubit picture is the one that's shown. And the results that we have are over here. The U1 gives you this process tensor matrix. The U2 gives the other one. The idea is if you multiply these two process tensors, you should get identity. And as you see over here, the 0, 0 element corresponds to the identity, and that's precisely what we get. Everything else is destroyed, which verifies that indeed our encoded versions are anti-commuting with one another. So now let's get to the main step, which was that we want to simulate our fermionic Hubbard model. And since we are considering just two modes and spinless terms, this is what it corresponds to. But note that in this model, the terms in the Hamiltonian don't commute with one another. So we need to do trotterization. And the trotter step for every term is the one that's shown over here. I would also like to mention that these V and U terms are important because they correspond to whether you have interaction or not. So by changing the intensity of V and U, you can change how strongly interacting your system is. Delta T is the Trotter step that you are evolving this for. So we can change n from 1 to infinity, but in general, infinity is we don't work till infinity. Our n goes up till 11 or 12, as we will show later.
Yep, so when we implement this, we're going to implement this starting with some given initial state. And so as Maryam said, because our coefficients u and v both equal 1, or they're both just the same value, the ideal result, if you are trying to simulate over some t over infinitely many steps, is a perfect sinusoid with these 1, 0 and the 0, 1s switching back and forth, which is what we expect. But when we run this in an ideal simulator, so over here, we're running it on a probabilistic ideal simulator with 11 steps over a time over t equals 2, we do get the sinusoidal pattern we expect, but it's going to be more coarse since, again, it's a finite number of Trotter steps as opposed to infinitely many. When we then take this and run it on a noisy simulator, and this case is the ARIA QPU probabilistic noisy simulator, we do get the general pattern we expect. This is for n equals 10, t equals 2. But we don't get the sinusoidal relationship due to the induced errors. So something we'll get into later is how do we figure out, how can we break down these errors in terms of our Pauli basis vectors. So yeah, if we then focus on specifically one of our steps, so I picked time equals 1, which corresponds to the 10th Trotter step. A way in which we can extrapolate this error channel is by running this circuit with its inverse. So this is the circuit with its inverse. And as we know from class, in an ideal environment, we would only expect the output of this. We would expect the output of this to be the identity, and any other extraneous terms we see are going to be introduced due to noise in our system. So when we run our circuit in an ideal environment, we do get the identity. You might ask, why don't we get 1 times the identity as opposed to 0.98? The reason for this is the ideal simulator we were using was a probabilistic one and was not a state vector simulator, which means it was still running finite shots. And because it was running finite shots, it's never going to be perfectly equal, hence the 0.98. However, when we take this circuit and run it in a noisy environment, this time on the IBM Perth noise model, which is a state vector simulator, we don't get just the identity. We get many other superfluous terms, and these terms correspond to our error channel, with the coefficient from in front of our identity going all the way from virtually 1 to about 0.32.
Okay, so in order to understand what the error channel corresponds to, let's start with a somewhat simpler error model. So suppose that I have a bit flip error that's added to every single qubit gate. Then if, let's say, I fix my probability to be 0.1, then that error channel in the process tensor for that is given as here. And in the fermionic picture, this corresponds to just the same thing, except that the x's are represented by these sort of non-local strings, and the z's correspond to local Majorana operators. But something interesting happens if we keep increasing p. So if we increase p, our channel shifts from single qubit errors to multi-qubit errors. So for p equals 0.3, you see that not only do we have single xyz terms, but also xx, xy, and xz terms. And this is showing us that even though initially we had an IID bit flip error, because as that error propagates through the circuit, this becomes something that's no longer IID, because you have 2 qubit gates inside the circuit. And so thinking about this in the fermionic picture, it's also interesting that if you have only single qubit errors, that is just extensive in the number of qubits. But for 2 qubit errors, something interesting happens, which is that if you have let's say I am considering xi plus 1 kind of errors, then that is a local term, and similar results follow for yy and zz terms. What we have learned in this project is basically that there's a nice connection between noise and simulation. So as I've already mentioned, there's different kinds of noises. There can be uncorrelated errors or correlated errors. So as we saw that if I have just a single qubit depolarizing noise, that corresponds to something that's non-local in the fermionic site. But if I have something that is correlated, which was coming out of the noise channel that we actually saw by running the INQ device, then that corresponds to something that is actually local on the fermionic side. So what this tells us is that we need to be able to characterize noise better, because this tells us what our hardware constraints are. And in turn, these hardware constraints inform what choice of encoding is the best. So for over here, we use Jordan-Wigner, which works well for these correlated 2-qubit errors, but not so well for single qubit errors. But at the same time, there are different choices of encodings that you can make. And this is a very active area of research as well. But what we would like to understand in the future is, well, how are the two related? If you're looking at a larger model, what are other methods of characterization that you can use other than process tomography? And so this is basically where we are stopping, but we have a good entry point to this project. And hopefully you liked our presentation.